So here we have the one-dimensional kinematic equations. So we have four equations here. And what these equations describe is the motion of some object. So it describes the object's position, velocity, acceleration, and the time of its travel. And the key thing to remember is these are one-dimensional, so they're used to describe motion in either the x or the y direction. So say we have some particle moving along the x direction, so it moves from this point to that point. And this is the positive x direction here to the right. We can use these equations then. And same if it's moving in the y direction. So say it's moving up now, and we're going to call the up direction positive y. Okay, so say it's moving here and then up here. Okay, so then we can use these equations now because it's moving just in one dimension. So by one dimension, it means either in the x direction or the y direction. So you could also move down. So it's going to be in the negative y direction because we're assuming up is positive. And then to the left. So to the left, that's going to be in the negative x direction. So these equations can be used to describe motion in either of these four directions. Now, if we had to describe two-dimensional motion, which means motion in both the x and y direction, we'd have to modify these equations slightly. But for the purposes of these problems, we're just going to assume that there's motion in just one of these directions. So it's either motion in the y direction, either up or down, or in the x direction, which is either left or right. So what do the variables in these equations mean? So like I said, we have position, velocity, acceleration, and time. So for initial position, that just means the position that you're starting at before the object moves. So you could say, let's assume we're starting at the center here. And then we have some object that moves to the right to the point over here now. So it's moving from the center to the point over to the right here. So the initial position is at the center here because that's where it's starting. So this is di. And now it's going to move to the right here. So this is going to be the final position, df. Now we also have the initial velocity and the final velocity. So velocity is just a speed, okay? So it's how fast something's going. So initial velocity is the speed that the object is going at its initial position. So at this point here, we have a vi. So it's an initial speed. And then the object is going to move to the final position df, and it's going to have some other velocity vf. Okay, so the initial velocity is the velocity at the initial position, and the final velocity is the velocity at the final position here. So now we have acceleration. So acceleration is how much the object is accelerating between its initial position and its final position. Now, we don't actually have an initial and a final acceleration because for these equations to work, we have to assume that acceleration doesn't change over time. So what that means is the acceleration is going to remain constant. It's not going to change when we go from this initial position to the final position. It's going to have the same acceleration throughout that position change. So A has to be constant for these equations to work, meaning it doesn't change. So what about the units for these variables here? So the units are what the variables are measured in. So initial position and final position are measured in meters. So we're using meters instead of feet because we're going to use the metric system for these problems. And then initial velocity and final velocity are going to be measured in meters per second. And then the acceleration is going to have units of meters per second squared. And then the time is going to be measured in seconds. And let's say we have a constant velocity. So a constant velocity means that the velocity is not changing with time. So basically the initial velocity is going to be the same as the final velocity. So if we have that case, we can write the velocity as the change in distance over a change in time. So this triangle here means delta, well, which means change. So this is written as change in d over change in t. And the change in the position, d, is going to be the final position minus the initial position. Because if we subtract the initial position from the final position, that's going to give us the change in position. And then for the change in time, that's just the amount of time it takes to go from the initial position to the final position. So that's just going to be t. So that's the case if we have constant velocity. So we have constant velocity when the acceleration is 0. So a is going to be 0 in this case. And then in a later video, we'll talk about what happens to kinematic equations when acceleration is 0. But like I said, for these problems that we're going to be going over now, we're going to assume that we have constant acceleration. So for constant acceleration, we have a equal to the change in v over the change in t. So the change in velocity over the change in time. And the change in velocity is going to be the final velocity minus the initial velocity. And then that's just divided by the change in time, t. So generally to solve problems like this, we're given some values for these variables, and then we have to find another value. So for example, let's just say we have some object starting at an initial position here, and it's going to some final position here. And let's say we're given the initial velocity and the final velocity and the amount of time it takes to cover that distance there. And then we want to find the acceleration during that time of travel. So we have to write down what we're given in that problem, and then we'll write down what we're trying to find. Let's say we're given the initial velocity, which is vi, the final velocity, vf, and the amount of time it takes to go from the initial distance to the final distance here. So we're given t. So we're given these three variables, and let's just say the problem we're doing asks to find the acceleration. Okay, so we're trying to find a. So if we're just doing this general example here, we're given these three variables here, and then we're going to try to find the acceleration. So we can just pick the equation here that contains all those variables, which would be this one here. So what we can do is if we're given these three variables, we can plug in their values in this equation and then solve for the acceleration. So that's how you do a general problem then. But you may need other equations here. So say you're given a few variables and you can't find an equation that contains all of them, and then you have to actually pick two equations then. Okay, so you may have problems where you have to find two different equations to solve for the unknown variable. So those are a little more complicated. So now this is just the introduction. So for the 5 problems that will be coming up here, they're going to increase in difficulty. So the first one's going to be the easiest, and they'll gradually get more difficult, and then 5 is going to be the hardest problem. So what we'll do is we'll apply what we learned here to actual examples with numbers, and hopefully we can apply what we learned here to solve some problems then. And again, for these upcoming problems, we will assume that the acceleration is constant. So we're going to assume that we have constant acceleration here for the upcoming 5 problems.